Good morning. Today we're going to learn a little bit more about relative frequency, and in particular we're going to look at fairness.
Can you remember when we roll a die, what's the exact probability? So the theoretical probability is that we might get a number 1.
Well, if you remember what the formula for calculating exact probability is, so we don't actually conduct an experiment, I won't be rolling my die to find out. All I needed to do was to look at how many there are of what we are interested in, our desired outcomes. So how many number 1s are there on a die? Well, there's just 1. And then we had to divide that or put it into a fraction with the number of total outcomes then on the bottom. So the possible numbers on a die are 1, 2, 3, 4, 5, and 6. So there's 6 of them. So 1/6.
Now, can you remember what the probability of it landing on a 3 is? Did you say 1/6? Correct. In fact, all of the numbers on a die has the same probability of it landing. And what that means is that there is an equally likely chance that when we roll the die, it could land on any one of those numbers. And that means that it is fair. And how can we be sure, even more so, that when we roll, it is just as fair and just as likely to get a 2 as it is a 3, a 1? Well, there's actually something quite unique about the design of our die. If you notice, and if you have one at home to look at, that's even better. What do you notice about the numbers that are on opposite ends of the die? 5 and 2 are opposite here. What about this one? 1 and 6 are opposite, so top and bottom. If I turn it this way, then 3 is at the top and the opposite is the bottom. 4, 3 and 4, 1 and 6, 2 and 5. Have you figured it out? They all add up to the number 7. And what that means is that the weight distribution of our die is completely balanced, so that when it is rolled, it really is completely fair. Now, of course, there are unfair die, and they're called loaded dice. And a loaded dice has some kind of weight inside, which means that when we roll it, the weight would be more likely to land against the table, and then the opposite number would be showing up on the top. And those became in existence many years ago when people would gamble and use dice and, unfortunately, try to cheat. So on a fair die, which is unbiased, there are equally likely chances of each number being rolled.
Your first letter is S.
And likewise with our coin, it is just as likely that we would get heads as it is a tails. So when we actually flip a coin, then we can say that that trial is fair. And here's another fair trial. If I spin this spinner, it is just as likely that I could get a blue as it is a yellow, a red, or a green. And that's because the same size sectors are there for each of the colours. So that would be a fair trial too. So if all outcomes are equally likely, then we can say that it is a fair trial. In our last lesson, we learnt about relative frequency, that sometimes we can't measure the exact probability, the theoretical probability, because it's quite hard for us to determine how many desired outcomes we have, the numerator for our fraction answer. So with relative frequency then, or experimental probability, in order for us to get an estimate of probability, so it's not going to be 100% accurate, but it's going to be a rough guide of how much the probability should be, we would actually have to conduct an experiment. So theoretical probability, we don't conduct an experiment. We simply observe and record desired outcomes over total possible outcomes. But relative frequency, we must actually conduct an experiment. So we actually roll the die many times, conducting many trials. The more trials that we conduct, the more accurate our estimate of probability will be. And with relative frequency, we would actually spin the spinner many times, recording down all of our results and then calculating how many did we get of what we were interested in. So if we wanted the relative frequency of getting a blue, I would record down how many times I got blue out of how many trials, how many times I spun the spinner. So it's important, therefore, that when we're dealing with relative frequency, to estimate our probability, that our trials are fair, and therefore that we have just as likely possibilities of getting each of our outcomes.
What about this spinner? If I spun this spinner once, would each of the outcomes be equally likely? No. And that's because there is a far greater amount of our circle, our spinner, representing red, and much less amount of space representing blue, which suggests that it would be more likely to land on a red and less likely to land on a blue. So this trial, the spin of this spinner, would not be considered fair. And what that means is then that we would expect to get a relative frequency for each of these different colours that were not equal. Your second letter to record down is A.
We learnt that the more trials that we make when conducting experimental probability, so let's say I wanted to calculate the relative frequency, so an estimate of probability, when I spin this spinner. Now this is the fair spinner again, so each of the colours have the same amount of space, so therefore it is a fair spinner. Now we would expect, providing we have conducted enough trials, the larger amount of trials, the more accurate our estimate of probability is. Well, we would expect then that if we did enough trials that we would get the exact probability, which we know is 1 out of 4. So my theoretical probability of getting green is 1/4. There is 1 green sector out of 4 possible outcomes, 1/4. And it's 1/4 for yellow, 1/4 for red, and 1/4 for blue. So the idea is with relative frequency, the more trials we do, so we actually record down what we get. Eventually, once we have conducted lots and lots of spins, we will have a relative frequency of also 1/4. So the idea is that we can identify if a trial is fair by looking at its relative frequency. If I ended up after 500 spins getting much more reds than other colours, then this would be a good indication that there's something wrong with our spinner, that it may not be fair after all. Perhaps there might be a little magnet underneath the red section.
Therefore, we would expect to have much different relative frequencies for our unfair spinner. We would expect to have a much larger relative frequency for red and a much smaller relative frequency for blue. So when we can see that something isn't fair, then it's much more obvious and we understand why the relative frequencies won't be equal. However, sometimes in a question, we might not be given the diagram. We may just be given the relative frequencies. For example, we might be told that when rolling a die 1,000 times, so that means the number of trials was quite significant. So we should expect to have relative frequencies that cancel down to roughly the real, true, theoretical probability of 1/6. So roughly every 1 in 6 rolls, we got the number 2. But if the results showed that the number 2 had a much higher relative frequency, so it was landed on many, many more times than the rest of the numbers, then we could actually say that that suggests that it's not a fair die.
Right, let's see if my spinner is fair. So I'm going to use relative frequency, which we know means to conduct an experiment. And in order to conduct an experiment where the results are as accurate as possible, I'm going to need to do as many trials as I can, lots of trials. And of course, a trial will be a spin of my spinner. So I'm going to do lots and lots of trials and record down my results of how many times my spinner, so the arrow part here, it lands on different colours. And we should then determine the relative frequencies and see if they are roughly the same as each other. And we expect that they should be close to 1/4 each, or 0.25, if this spinner is fair. Red, 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 yellow, red, yellow, blue, red, green, yellow. 15 hours later. Okay, so we have some results. Now, I span the spinner 1,000 times. Okay, so we can pretty much say that 1,000 trials is a pretty good amount of trials. So we should therefore be able to determine whether this spinner really is fair or not. So the idea is that we're going to now calculate the relative frequencies, which we can do because that's based on the results when you've actually performed an experiment. And that's what I have done here. And that we should then look at those relative frequencies to see whether they are all roughly the same and close to the theoretical probability, the exact probability, which we know is 1/4, or 25%, or 0.25. Let's have a look. Okay, so let's remember that the relative frequency then, our estimate of our probability, is where we take each of the colours that we're looking at. So let's say blue, we'll start with blue to begin with, and we record how many of the results we actually got blue for, and then out of the total number of trials. So the number of blue, so I spun the spinner and it landed on blue 230 times out of the 1,000 times it was spun. And that's a fraction which can be cancelled down, or alternatively, we can create it as a percentage or decimal. And I have it here as a percentage, 23%. Now remember that we are roughly expecting it to be 1/4 for 1/4 of the trials to land on each of the colours, because each of them are equally likely with an amount of space, and therefore 1 out of 4 is the theoretical probability. Now, 1 out of 4 is a quarter, 25%. This is 23%. That's fairly close, so at the moment, it looks like perhaps it is fair. Let's carry on and work out the relative frequencies for the rest of our colours. Okay, so I have calculated the remaining relative frequencies for green, yellow and red. So the number of times we got green in our experiment out of how many times I span the spunner. 180 divided by 1,000 and 18%. Of course, if I wanted to keep it as a percentage, I can simply cross the 0 off the top and the bottom, and then it will be 18 out of 100. That's the effect of dividing the top and bottom by 10. Or finding the equivalent fraction as with 100 on the bottom, which is what we know is the requirement to get percent. Percent mean out of 100. So let's have a look. Well, the yellow relative frequency is exactly what we were expecting, 25%. And that's what we would like to see all of them to be roughly around that if it was to suggest my spinner was fair. However, if we look at the relative frequency for red, it's 34%. Now, 34% is a great deal bigger than 25%, the exact theoretical probability. The fact that not all of our relative frequencies are similar, despite the fact there was a high number of trials, is sufficient enough information to decide that this spinner is suggestedly not fair. And in truth, I actually have a little bit of sticky stuff under here, which is making it tilt slightly, and therefore it was landing on my red a little bit more often. In an exam, we might be asked to write down the reasons why we believe that our trial or experiment is either fair or unfair. And this could be what you might write down. Well, if the spinner is fair, then the relative frequency for each sector should be close to 25% after a large number of trials. As the relative frequencies are not all close to 25%, we can conclude that the spinner is not fair. Note that the spinner was spun 1,000 times. This is a large number of trials, so we can be confident that the relative frequencies are close to the actual probabilities. Your third letter to record down is R. Notice that the words biased and unbiased might be used. If something is unbiased, then it means it's fair. Whereas if it's unfair, then it's biased. For example, I might be deemed to be biased if I was to say 1-4 and 1-6 are the greatest first-year classes of all time. Well, although that might be my opinion, but it seems unlikely that that really is true, and therefore we would say that it is biased. It's unfair. I haven't taken into consideration enough facts or even studied or taught all the other first years that are out there in existence, so I would only be able to make my judgment on a very few that I have taught, and therefore we definitely can't say this is fair. Likewise, if you were to say that your football team were the greatest in the world, well, there's lots of people that would probably disagree with you, so that would be classed as a biased statement, an unfair statement. So my spinner, it looks like it might be unbiased, fair, but we actually determined through calculating the relative frequencies that it is actually biased. It's unfair. Before I send you off to do some questions yourself, let's have a quick look at this question that's in your textbook on page 132, exercise 8.5. Question 3. The spinner shown is spun. It says for part A, what colour would you predict that the spinner is more likely to land on? What do you think? Well, hopefully you said red. But you wouldn't have full marks yet, as the question continues to say, give a reason for your answer. So our reason would be that there is a greater amount of area or number of sectors that are red compared to blue. There are 3 red sectors representing 3/4 of the circle, and there are just 1 that are blue, 1/4. Part B asks us to explain how we can change the colours on the spinner so that each colour is equally likely to occur. What do you think? Well, for it to be equally likely, then we need to have the same amount of sectors representing each colour. So we can simply change one of these reds to a blue, and that way there will be 2 blues and 2 reds. Okay, let's roll a die. We're going to try and see if this is a fair die. So we're going to record what we land on, but I'm interested in particular in the number 2. So out of 800 rolls, so yes, I will be much older when I finished. How many times did it get? Number 2. And we're going to calculate the relative frequency, and then we're going to look and see, is it what we would expect it to be? So is our relative frequency close to our theoretical probability, what we know that getting a 2 should be? And we know that the probability, theoretically, of getting a 2 is 1/6, which as a decimal is 0.16 recurring, or as a percentage, 16.6 recurring percent. Now, you can always use an online roll die roller. There are lots of them available. You can Google them, such as this, if you don't have any dice yourself at home, and you can experiment around with it yourself. So number 3, number 3, number 6. Why don't you have a go at creating some relative frequencies and see how many times you might actually have to roll a die for you to eventually get a relative frequency that is the same as its exact probability to get 1/6. Okay, so the results are in, and 300 of my 800 rolls landed on the number 2. So let's create the relative frequency. We know that's how many of what we are calculating the experimental probability of. So how many 2s did I get? 300 over the number of total trials. So in this case, how many times I rolled the die? 300 over 800. Now that cancels down. I can divide the top and the bottom by 100, simply cancelling out the same number of zeros on the end, to 3/8. Or, as a percentage, 37.5%. 0.375 as a decimal. Now, in comparison to the exact probability, there's a big difference there. Notice how sometimes you might have to change from either the fraction to the decimal or to the percentage to have a really better understanding of comparing two. When you have a 1/6 and 3/8, it's not quite as obvious how close together, or in fact how far away those are. But when we convert them to a percentage, we can see that 16.6 recurring, which of course means 16.666666666. Now we could round that up to 17% to the nearest whole number, is a lot smaller than 38%, which is 37.5% rounded to the nearest whole number. This great difference suggests, therefore, that this die is biased. Now, in reality, if you would like to have a go at doing some of these experiments yourself,
you do not need to have to roll a die 1,000 times. If you go to rolladie.net, which is this website here, you can actually pick, first of all, how many sides you would like your die to have. So this is one die with 6 sides, and I would like to roll it not once, but 1,000 times. I want to see my totals and press go. Now it has rolled the die 1,000 times, and if I scroll down, it's showing all of my results, but it's going to still take me a long time to calculate all of those. So thankfully there is a show the stats, and there we have it. It's told us exactly how many times it landed on each of our numbers. Now we know that if the die is fair, that those should all be roughly the same. And not only that, but if we've got sufficient enough number of trials, that they should have relative frequencies that are close to the theoretical probability of rolling a die, so close to getting 1/6. Now that means that 1/6 out of the number of times we roll, we should get each of those numbers. Now, if you wanted to calculate what 1/6 of 1,000 is, because we rolled the die 1,000 times, or we can do that quite easily. Can you remember what the word of in mathematics refers to in terms of an operation? It's multiplication. So 1/6 of 1,000 means 1/6 times 1,000. And that's the number 166. So if the die is fair, the exact probability is that each number would be rolled on 166 times. It's just like we divided 1,000 by 6. How many times will each of them get that answer, that result? Now, let's have a look. Wow, it's actually pretty close. All of these numbers are not too far from 166. A few are a little bit under and a few are a little bit over. I conclude, therefore, that this die and this die generating website has used a fair die.
For your homework, I have set you 3 questions from exercise 8.5, page 132. Question 1 about flipping a coin. Question 5, rolling a die, and also rolling a die for question 7. Thank you for listening, and I shall see you in class tomorrow. Have a good day.
Just for fun, why won't Miss Foley drink a glass of water with 8 pieces of ice in it? Because it's 2 cubed. Get it? 2 cubed means 2 times 2 times 2, and that's the number 8.